Welcome to this number theory primer. In this lecture, we look at the division with remainder theorem and let us review some basic notations. So this is the notation for the set of the natural numbers. Natural numbers start with 1 and they go like this 1, 2, 3 and so on. Then we have the set of whole numbers. So it is denoted with the notation for natural numbers appended with the 0 in the subscript. And there are other notations, but I use this. So this is basically 0, 1, 2, 3 and so on. They start with 0. And then we have the set of integers, which are all negative integers. I mean, all the, what can I say? I mean, all the negative integers and 0 and the positive integers. So these are some notations. And also let us look at some basic shorthands. So this symbol is a shorthand for there exists. So one may see things like there exist. Wait a second. Yeah. So one may see things like there exists X. That's a very horrible color. There exists X such that something happens. So that kind of. So instead of writing there exists X, it's just easier to write this. But it means exactly the same thing. There's nothing deep going on. This stands for all. So one could say for all X in some set in, let's say, natural numbers or in N, something happens. I mean, some statement, that kind of thing. This is the notation for belongs to. So or lies in. I mean, this can be read in several ways. It means the same thing. Sometimes one may read it as belongs to, sometimes lies in, sometimes is a member of. So for instance, what happens is if we have a set A and we write this, we mean X is an element of A or belongs to A or lies in A, is a member of A. There are several ways to read it, but this is basically the template where it is used. This is the Greek symbol phi. It could be used just as a Greek symbol phi, or many times in context it is used to denote the empty set. Empty set is the set with no elements in it. This is the notation for is a subset of. So one writes A and then makes that symbol and B to read that A is a subset of B, meaning every element in A or every member of A is a member of B. The next one is notation for is a proper subset of. So when we write this A and then that, we just slash out this. We slash out the one at the bottom here. So this is meant to mean that A is a proper subset of B, meaning A is a subset of B first of all, but A is not equal to B. And this is basically why this notation has been chosen. This is the notation for is a superset of. So if we write this, we just mean A is a superset of B, which is equivalent to saying that B is a subset of A. And similarly, you can come up with this cousin of the same notation. So these are some basic things. And now let us also look at what is called the well-ordering principle. It's a very fundamental statement in mathematics. So it says that if we have a subset of natural numbers which is non-empty, then S has a smallest element. So let me expand on what I just said. When I say S has the smallest element, it just means that there is some element in S which is at most every other element in S. That's what it means to say that it has the smallest element. And this is a very, very obvious statement. If you just think about it, you can just try. You can take a non-empty subset of the natural numbers and you'll automatically see that this is true. I don't think this can be proved in any reasonable way. It's so basic and we will take it for granted. Here is an exercise. Show that the same thing holds for whole numbers. Whatever we just said for natural numbers also can be said for whole numbers. And you can further generalize in an obvious way. All right, so that's that. And now we can get to the material of this lecture. We want to talk about division with remainder, and hence let us first define what is meant by division. So fix two integers a and b and assume that a is non-zero. We say that a divides b if there is some integer n such that b equals an. So whenever we say a divides b, we automatically have that a is non-zero, and we then say that, we define this as saying that there is some integer which when multiplied with a yields b. So that's the definition of division. I'm sure you're familiar with it from high school. So now there are some synonyms for the same definition. So suppose A divides B, then we also express the same thing by saying that B is divisible by A, or we say that A is a divisor of B, or we say that A is a factor of B, or we say that B is a multiple of A. As far as I can tell, these are the only 4 synonyms, but maybe there are more. All right, so that's that, and this is a very useful notation. If A divides B, we express that by writing this. So we make A and then a vertical bar and then B. So that's a convenient shorthand. And let us look at certain properties of division. So the first property is that suppose A divides B and B divides C, then A divides C. This should be obvious, but I encourage you to write down a formal proof if you haven't done this kind of thing before. All right. Clearly, 1 divides every integer. So again, if you, I'm sure you see this, but it is a good idea to write a formal proof at least once in one's life. 0 is divisible by any non-zero integer, right? Because if you, let's say, take B as 0 and A is just some non-zero integer, then A times 0 is 0, and hence A divides 0. So that's clear. Every non-zero integer divides itself. That's what this says. You pick a non-zero integer, then it divides itself. So that's also clear. And lastly, suppose we have 2 integers, both of which are at least 1, and A divides B, then B exceeds A. Again, that should also be fairly obvious. All right, so let's move on. These are some basic definitions that I'm sure we knew from high school. What is a prime? So fix a natural number which is at least 2. We say that it is a prime if the only positive integers, or the only natural numbers, let me say, it's the same thing, but the only natural numbers which divide P are 1 and P. So P is a prime if the only positive factors of it are the number itself and the number 1. So in other words, it only has trivial factors, is what we are trying to say. You cannot kind of decompose it non-trivially. So here are some examples. 1 is not a prime. Whenever we say prime, we always mean a number at least 2. So 1 is not a prime, and then we start with 2, 3 is a prime, 5 is a prime, 7, 11 is a prime, 13, 17, 19, 23, and so on. 6 is not a prime. 6 is not a prime because 2 is a factor of 6 and 3 is a factor of 6, and they are both different from 1 and 6. So 6 is not a prime, and so on. So yeah, so that is the notion of prime numbers. And now let us prove the main theorem of this lecture. Fix 2 natural numbers, B and D. Then we want to say that there exist unique integers Q and R, such that B can be written in this fashion, dq plus R, and R is in this range. So you can read this as dividend is equal to divisor into quotient plus remainder. That's how you should read it. And this is a theorem that we've been using for, I don't know since when, but perhaps without realizing. So all this is saying is things like this. So suppose you have B equals 7 and D equals 2. Then all we are saying is something like this. So 2 is equal to 2 times 3 plus 1. So this is Q and this is equal to R. So you can see that these two things are satisfied if you take B equals this and D equals that. And there is no mystery here, but we will give a formal proof. So there are 2 parts of the proof. One is the existence part, the other is the uniqueness part. So first let us do the existence part. Proof of existence. Existence of what? Existence of Q and R. So define S as all these differences. B minus dq. Q is an integer. but we want to collect only those such things which are non-negative. So it may look complicated, but all we are doing is form all the possible differences of this sort where q is an integer, but collect only those which are non-negative. And note that b is a member of S, because if you take q is equal to 0, clearly then b is what you get here, and b is non-negative, so it is here and hence in S. So in particular, S is non-empty. So we have a non-empty subset of the set of whole numbers. Clearly this is a subset of whole numbers because you've intersected with whole numbers. So S is a non-empty subset of the set of whole numbers, and thus by the well-ordering principle, WOP stands for well-ordering principle, there is a smallest element in S. There is a smallest element in S, call it R. So in other words, R is the, this is just notational change. R is equal to minimum of S. That's how we may write it. Okay. So far so good. And here, since R is an element of S, note that, thus R is at least 0. Why? Because any element of S is at least 0. S is, after all, a subset of the set of whole numbers. Therefore, this much is clear. We claim that. Claim is that R is strictly less than T. So let's prove this claim. Suppose not. So if you want to prove something, you can go by contradiction. So suppose not, then R is at least D. And now say R is equal to B minus DQ for some integer Q. Why does such an integer Q exist? By definition of S. R is a member of S, and any member of S can be expressed this way. So that's all we are doing here. Therefore, R minus D is equal to B minus D times Q plus 1. Right. But here is the key point. R minus D is at least 0. Why? Because of our assumption that R is at least D, and therefore R minus D is at least 0. So this guy is non-negative, and this is of the form B minus D times some integer, and therefore R minus D is an element of S. This is a crucial part in the proof. We expressed R minus D as B minus D times some integer, so it's here, and at the same time we showed that it is non-negative, so it is also here, and hence it is an S. But R minus D is strictly less than R. D is positive, and hence R minus D is strictly less than R, and that's a contradiction because R was the smallest element of S. And here what we have shown is that there is something smaller than R lying in S. So that's a contradiction, and hence our claim is proved. So let me just maybe mention it, contradiction. So we have proved the claim, and with the claim, it is the existence part is clear because just take R is equal to, R is equal to B minus D times, R is equal to B minus D times some integer. Again, R is a member of S, and any member of S can be written this way. And now if you just shuffle it around, it gives us B is equal to DQ plus R, where we already showed that R is in this range. So that proves existence. Now we will prove uniqueness. That is actually much more straightforward. So suppose B is equal to DQ1 plus R1 and B is equal to DQ2 plus R2 with, so for some integers Q1 and Q2 and R1 and R2 with the condition that R1 and R2 are lying in this range. So want to show that Q1 equals Q2 and R1 equals R2. This is what it means to say that there exists unique Q and R. This is exactly what it means to say that. So this is what we want to show. But by using these two equations, just subtract these two equations, we get 0 is equal to d times q1 minus q2 plus r1 minus r2, which implies r2 minus r1 is equal to d times q1 minus q2. And if q1 were not equal to q2, what you can do is take absolute values on both sides. Then, I mean, you could take absolute values even without having to have q1 not equal to q2, but then r2 minus r1 absolute value is equal to d times q1 minus q2 absolute value. D is already positive, so there is no need to write absolute value around d. And here then it follows that r2 minus r1 is exceeding d. But that's not the case. This is a contradiction because r1 and r2 are in this range, so their difference cannot be exceeding d. This is a contradiction. And therefore, q1 must be equal to q2, and hence r1 is equal to r2. So thus, I mean, what we wanted to show has been shown. This contradiction shows that this assumption cannot be true, and hence q1 is equal to q2, and it automatically then follows that r1 is equal to r2, and that's the proof of uniqueness. So the real crucial part was the proof of existence, and that is also a very, very natural thing, although perhaps the way I presented it, it may give the impression that it's something complicated, but it is not. Just think about it. So I think that's it for this lecture. Yeah, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.